Hello and welcome. This is part 4 of our 5-part series on basic skills mathematics review. And in this video, we're going to cover basically the building blocks of algebra and eventually work our way to equations and inequalities. In this page, we see how we basically develop algebra. We start with constants, which are basically quantities that do not change. Examples would be like 0, -12 pi, a half, 3 1/4, etc. Then we bring in variables. This is where the magic of algebra begins. Quantities that can vary or change. Examples, we use symbols for variables such as x, y, letters of the alphabet or letters of the Greek alphabet are commonly used, alpha, beta, etc. And by using those constants and variables, we create some expressions. We multiply some constants with various powers of these variables. And these are, of course, the simplest kinds of algebraic expressions. They're not the only kind. They're the kind we're going to study initially, but we'll get to more complex types later. These particular simple types are called polynomial expressions. And then we take an equal sign, put one expression on one side and one expression on the other side of it, and we end up with equations, which we can then solve for the variables that are involved in that equation. So just to give you a quick overview of how algebra is developed and where we're headed. One of the first things that we need to understand with algebra is the concept of like terms. Of course, before we can tell you what like terms are, we need to tell you what a term is. And again, we're focusing on simple types of variable expressions called polynomial expressions. So a polynomial term is a product of a constant and a whole number power of variables. The general form of a polynomial term is in one variable is given by ax to the n for basically real variable x belonging to R, and which is the set of real numbers. And we need, this is the important part here, we need the exponent here to be a whole number, and that, remember, includes 0. So we remember what the set of whole numbers is, and we have this set containing 0, 1, 2, etc. Okay, so the exponent of these variable parts need to be powers, I should say, need to be whole numbers. Now, each part of ax to the n has a name. The a is called the coefficient. It's just a constant number that's multiplied by this variable power. The n is called the degree. We normally call it the exponent, but in the context of polynomials, that's called the degree. And x to the n as a whole is called the variable part of this particular term. All right, here we can see some examples of polynomials in one term, or one variable, I should say. 5x, 6y cubed, -3/4 y to the 7. While we'll mostly be concentrating on polynomials in one variable, there are polynomials that can have more than one variable, as you can see some examples here. Notice that all the variables in the various expressions have whole number exponents. Okay, so we're finally ready to define like terms, and like terms are basically terms whose variable parts are equal. If you recall, when we defined the expression of the type ax to the n, we said this part is the variable part, right? Including the base and the degree, right? So this part, the coefficient, can be different, but as long as these parts are the same, we consider two terms to be like terms. Now, notice that sometimes they may look superficially different, right? The variable parts, but as long as they're fundamentally equal, we consider those to be like terms. So these two, even though the variable parts look somewhat different right in here, they are considered like term because the like terms because the criterion is met. Since we know that x times x times x is indeed the same as x cubed. Let's go ahead and take a look at some like terms as well as some terms that we need to be careful about. Now, notice that these two are definitely like terms because we're not concerned about the coefficients being different. We just want the variable parts to be the same, and they are. The same is the case here. Now, the order here is reversed. You have v to the 4 u to the 5th here and u to the 5th v to the 4 here, but remember, by the commutative property of multiplication, those two are considered the same, so therefore these would be like terms. Here we have two terms that are not alike. Even though they may kind of look alike, they're not, because u squared and u cubed are not the same thing. Just consider regular numbers. Is 3 squared the same as 3 cubed? Of course it's not. 3 squared is 9, 3 cubed is 27. So these two would not be considered like terms. Okay, here we have two more like terms, and notice that the variable part of both is x. Yeah, they have more complex coefficients, but that doesn't matter. Same here, we have two variable parts that are more complex than just say x, but nevertheless they are the same, and therefore these two would be considered to be like terms. Now here we have two terms whose variable parts are the same, but obviously they're not polynomials, so we consider this to be like terms, but they're non-polynomial like terms. These two, of course, even though they have a lot that looks the same, are not like terms because we only care about the variable parts, and the variable parts are different. Like terms are extremely important to us because we can use them to combine and simplify expressions. The way we combine like terms are by applying the distributive property in reverse. The distributive property, as we know, is as follows, and when we go from this side to that side, that's called multiplying, but we're going to be going in the opposite direction, which we will call factoring. We're particularly interested in this version, the right distributive property. Again, when we go from here to here, that's called multiplying, but when we're gonna go from here to here, that will be called factoring. Now consider how we can use this property to factor this, because notice we'll go ahead and take the x out just like the a was taken out here, factored out, and that leaves us with 3 plus 5, which is 8x. So this is the kind of thing where you go, I knew that, I didn't have to go through all that to get the 8x. Yeah, but remember, this is where we're going to start to worry about the fundamental nature of things and why they are the way they are, not just based on what we already know how to do. And there we have. And also with simple expressions like this, yes, you can skip it. But if you have really complex fractions, you really may want to take the time to do this business before you proceed. Okay, here we're going to go ahead and combine like terms to simplify this expression. If you already have a good idea how to do it, go ahead and try it, and if not, you can go ahead and watch. But I do think every one of you should be able to get some progress with this at least. All right, so we noticed that we have like terms here and here. Those two would be considered like terms, and these two are like terms as well. So if I put maybe a single mark under these and a double mark under those, there we have our like terms. So notice that what we can do is we can put the x squared terms next to each other and go ahead and factor out the x squared. So 1/2 minus 3/4 x squared, and then put the -5/6 minus 1/6, and that's going to be multiplied by x. Okay, so in here we have two unlike fractions, so we need to go ahead and find the common denominator, which we know is 4, and of course this 2 is going to have to get this multiplied by 2, and the same with that 2. So we end up with 2 minus 3, which is -1/4 x squared, and these two, of course, -5 minus 1 will give us -6/6, which is -1, times plus will continue to be -1, so we'll just say minus x minus 1x, which we can just usually leave as x. And that's how you would simplify an expression like that one. Now, a mathematical equation, as mentioned earlier, is composed of an equal sign with a mathematical expression on both sides of that equal sign. Here are some famous mathematical equations to consider. One of the nicest equations from mathematics is what's called Euler's formula. E to the I theta equals cosine theta plus I sine theta. There are some really significant numbers here. E itself is a constant, I is a constant. It's the square root of -1, and we have this really beautiful formula from the subfield of complex analysis. Here's probably the most famous equation in of all time. E equals mc squared, which is Einstein's mass gravity equivalence formula, and it's from physics. The subfield would be special relativity. And here's another really famous equation, namely the Pythagorean equation, and it comes from the field of mathematics and the subfield of geometry. We're going to go ahead and begin our study of equations by learning how to solve first-degree polynomial equations known as linear equations. Any equation that can be written in this form is basically a linear equation. The only restriction here being that a, which is the coefficient of x, should not be 0. These other two may or may not be 0. And these kinds of equations are called linear equations on one variable. The reason they're called that is because when you start to graph them using the Cartesian coordinate system, all the points line up. In other words, the y values change with respect to the x values at a constant speed. The following equations are all linear equations. Note that an equation does not have to be exactly in the ax plus b equals c form from the beginning to be called linear. You should, however, be able to put it into that form after some legal algebraic actions. So this one is obviously a linear equation because it's exactly in the form that we wanted. Not so much for this one. We would have to do quite a bit of simplification to be able to see that one, and the same here. What really makes them all linear is the fact that the variable expressions in each of them have no power other than 1. That's what makes an equation linear. All right, and so that's what they all have in common, these linear equations. Now, before we can successfully solve linear equations, we need to learn and understand a few more important properties. We already saw some in the last video. Here's a review of what we saw before. We saw the reflexive property of equality, the symmetric property of equality, the transitive property, and the substitution property. Now we need to add a few more properties to the list of properties of equality. The first one is the addition property, which says if a equals b, then a plus c equals b plus c, and that's for any a, b, c, or d belonging to R. And the fact of the matter is that any constant may be added to both sides of an equation. That's exactly what we're saying here. There's a second version of that. In this case, we have two equations, and what the property says is that we can go ahead and add those equations. Just make sure you add the left items together and the right expressions together, and this is also going to be true if, of course, these are true. And basically the corresponding sides of equations may be added. All right, so that's what we call the addition property of equality. Now, what I'm calling the subtraction property here, a lot of people like to handle within the context of the addition property, which is true because it's subtracting is just adding the opposite, but it's a little bit easier just to have it as its own property. So we'll state it differently as a different property, but do keep in mind that you could theoretically just use the addition property for this one as well. You're just adding negative numbers in this case. So this one says if a equals b, then a minus c equals b minus c. As long as you have a constant, you can subtract it from both sides of an equation, and that should keep the balance. All right, now the second version, very much like the other one for addition. If a equals b and c equals d, then a minus c equals b minus d. So in other words, you can subtract the corresponding sides, and that is considered to be a legal operation in mathematics. The multiplication property of equality is very similar. So that if you have an equation like a equals b, it's okay to go ahead and multiply both sides by number c, and that's one version. The other version is that if you have one equation, a equals b, another c equals d, it's okay to go ahead and multiply the equations. The division property basically says a very similar thing. You can divide both sides of an equation by the same constant. However, because you're dividing, you need the caveat that c should not be 0. And the same goes here. You can go ahead and divide, but again, notice that we should specify that neither side of the second equation should be 0 for this property to hold. All right, our game plan for solving linear equations in one variable is what we call the 3S approach. We're going to simplify, separate, and solve. As simple as that. So first, we'll simplify the expressions on both sides of the equation. Notice it says if necessary, because sometimes they're already simple. Next, we'll go ahead and separate the variable terms from the constant terms. Again, if necessary. Sometimes the equations are really simple and that's already taken care of too. And finally, we simplify again by combining like terms and solving the equations. And again, if necessary. Before we go any further, there is one great shortcut that is very easy to understand and can save us a ton of time. So we're going to go ahead and go over it right now, and I want you to consider what happens when you have some equation, simple equation like x plus 2 equals 5, which you can even solve in your head, and you subtract 2 from both sides. In other words, you're adding the opposite of 2 to both sides. Notice that you end up with x on this side by itself equals 5 minus 2, which will of course solve this equation for us and tell us x equals 3. Now note that we were able to move the 2 from this side to that side, and the way we did that brings us to the understanding that, hey, maybe we can always do that with any term. In other words, I can take any term, move it to the other side of the equation by adding the opposite to it, and it's going to change its sign. And that's where this expression change sides, change signs comes from. We're going to apply that shortcut very soon. Before we do, remember that the solution of an equation is the value of the or values, sometimes equations have more than one solution, of the variable whose substitution for the variable in the equation results in a true statement. We say that the solution of an equation satisfies the equation. For example, x equals 3 is a solution of x plus 2 equals 5, because substituting 3 for x in x plus 2 equals 5 yields 3 plus 2 equals 5 or 5 equals 5, which is a true statement. So 3 is a solution of x plus 2 equals 5. We can also say that 3 satisfies x plus 2 equals 5. Finally, we can present all solutions of x plus 2 equals 5 in a set called the solution set. And we often denote that by the script S symbol. This particular solution set only has one element in it, and that's 3. So we just put S equals 3, like so. We don't put the name of the variable in the solution set. All right, so here we're going to start to solve some equations, and notice that this is an extremely simple one, and we can add 2 to both sides, or we can apply our shortcut, because remember, we want to first simplify both sides. That's already done. There is nothing to do here. Then we want to go ahead and separate, right? So we have the variable here. It would be good to move this constant to the other side. And of course, we can do that and change its sign. So we get u equals -5 plus 2, so you end up with u equals -3. All right, now checking a solution is very simple. We're just going to plug that back into the original equation and make sure it's true. So remember, you always want to go back to the original equation when you want to check, not some equation along the way. All right, so -3 minus 2, we want to know if that's equal to -5. I'm going to put a question mark above that equal sign because I'm not asserting it, I'm checking it. Okay, And I noticed that the left side is -5, and of course the right side is -5. I can drop the question mark now because I've verified it, I've shown it, and now I can say that the solution set here contains only one element, and that's -3. All right, simple, right? All right, here we have another equation to solve. By all means, do try this on your own first. Notice that in this case, we do have simple expressions on both sides, so there's nothing to do as far as simplifying each side is concerned. So we go ahead and get ready for the move. Now, when it comes to equations, where do you move the variables to and where you move the constants to is completely arbitrary, but sometimes it's more helpful to do one thing rather than the other. Like, it usually is a good idea to check. Notice there's no simplification again because that's already, both sides are already simple. So since it's time to separate, you should look to see which of the terms containing the variables in this problem have the larger coefficient. We notice -8 is larger than -9, so that's where we decide to keep the variables on the right side. So we go ahead and we move the -9g to the other side. It becomes 9g, and we on this side we have 3, and we move over the 5, so we get -2 equals g, and that's basically it, except we want to check, so we're going to write -4 times -2 plus 3. We want to know if that's equal to -8 times -2 plus 5. Again, notice we have a question mark because we're checking. Now, -9 times -2, that's 18 plus 3, and now we're going to say that's equal to, that's 16 plus 5. We're still checking. Now we notice that's 21, and the other side is 21, so it checks out, and we can now confidently write that the solution set contains -2. Remember, we don't put the name of the variable within the solution set, just the values of the variable that make the original equation true. Here's another equation of an important variety, because when you see these, I would like you to see something hidden in there, and that is the fact that you have something expression or on each side of the form a over b equals c over d. As soon as you see those, you should think cross multiply, because that's a proportion, and therefore AD equals BC. Okay, so now what we're going to do to put it kind of more like in this form, if you want, you can write the top as -4x over 5 equals 3/5. Okay, so now we're going to go ahead and cross multiply, so we get -4x times 5 equals 3 times 5. Now we're ready to go ahead and apply the division property of equality to get rid of the -4 times 5. Notice I didn't even multiply it out because it'll be easier to cross cancel if you don't. Alright, so now I'm just going to put like so. Alright, so now we notice that we can do some cancellation. Here the entire -4, it cancels out. X is there still. On the other side, 5 cancels out, so it does here as well. So we end up with X equals -3/4. All right. So we could also solve it by multiplying both sides by the reciprocal of the -4/5, which is the coefficient of X. So we could go ahead and do it like this. Now notice that the reciprocal of -4/5 is -5/4. All right, so we end up with X equals -15 over 20. That is precisely breaking the golden rule of multiplication, right? Always see if you can cross cancel before you do that, and if you do, see how beautifully that works. You end up with -3/4, just like we did by cross multiplying. Okay, so that's another way we could have solved that particular equation. All right, so here's another equation for us to solve, and this time notice we do need to do some distributing first, and that's because there is an invisible one sitting right there that we have to distribute. Okay, so we end up with 6 minus 5k minus 7 equals -3k plus 8. Remember, simplify, separate, solve. We're in the simplify phase right now. We're still in it because we can now combine these two terms here to get -5k minus 1 equals -3k plus 8, and we go ahead and at this point separate. We notice that the variable expression with the larger coefficient is on this side, so we'll move the k's to that side. So remember, change sides, change signs. So I'm going to keep the -3k here. I'm going to move the -5k over, so it becomes plus 5k. I'm going to keep the -1 here, no change, but I'm going to move the 8 over to the other side, so that becomes -8. So now we get -9 equals 2k. So divide both sides by 2, I get k equals -9 over 2. All right, so you always want to check when time permits. I have put the requirements on each of these as we do these, but for the sake of keeping the lesson to a reasonable amount of time, I'm going to go ahead and do a quick check for you on a calculator, but These need to be done manually when you do them for your practice, but here, just to satisfy ourselves, we can do a quick check. So we're going to plug in -9/2 for k. So 5 times -9/2 plus 7. All right, and we're going to see what that expression is. That's 21.5. Now we're going to plug -9/2 into the right side of the equation and see if we get the same thing. So -3 times -9/2 plus 8. And we notice that we get the exact same number once we plug in -9/2 into for k in the entire equation. All right, so that was a quick check. That's the very least we should do when it comes to checking equations. Okay, next we would like to go ahead and categorize all linear equations in one variable. As it turns out, they break into 3 distinct groups, right? The kind of equation we've been solving so far with only one solution is just one of the types of linear equations that are possible. Those are called conditionals, such as this nice simple equation, x plus 2 equals 5. We know that this equation is true if x equals 3, and it's false if x does not equal to 3. So it's whether it's true or false depends on the condition being met, and therefore we get one solution, namely 3, and we can say s equals 3 like that in, of course, set notation. Now, when you attempt to solve it, of course, everything goes smoothly and you get yourself one solution. So conditionals have one solution. Then we get this type of an equation called an identity. Here's a very extreme case of it, you know, x plus 1 equals x plus 1. Obviously, that works for any x value, right? So it's true for all real numbers and it's never false. So that's exactly what we mean by an identity, an equation that's always true. So the solution set is basically all of R, which in interval notation becomes -infinity to infinity. I'm going to go over this notation in more detail later. If you attempt to solve such an equation, right, notice what happens. You get the x's on one side, the ones on the other side. You end up with 0 equals 0, which is an identity as well. This is always true, right? The last type of linear equation that we get is a contradiction. These ones have no solutions, so the number of solutions is 0. It's not that 0 is the solution. Be very careful. That's the number of solutions. An example is a very simple x equals x plus 1. This equation is just asking for too much. Remember, just because you have an equation, it doesn't mean it's possible to solve, because there's no way you're going to find a number that doesn't change if you add 1 to it. So therefore, this is always false for all real numbers and never true. That's the exact meaning of what a contradiction is. And in this case, we say the solution set is the null set, which we write like that, which means also the same as this, which is the empty set, and they're the same thing. When you try to solve one of these, notice what happens. Get the x's on one side, one number on the other side, you end up with 0 equals 1, which is indeed a contradiction. You know, identities and contradictions aren't always going to look so simple. They could be in disguise. We'll see one or two later. All right, so here we're asked to solve and categorize. So we have 20 times x minus 4 equals 10 times 2x minus 8. The first thing I notice with an equation like this is the obvious fact that both sides of this equation are divisible by 10. Anytime I can get rid of a constant to make my life simpler, I'm going to do that. So the very first thing I'm going to do is I'm going to go ahead and divide both sides of this equation by 10. Right away, that makes life simpler by making this become a 2 and this become just a 1. All right, so now we notice that we get 2 times x minus 4 equals 2x minus 8. So therefore 2x minus 8 equals 2x minus 8. Now we already have enough to go ahead and claim that this is an identity, but it is nice if we can just get to an identity with no variables in it, and that's very quick and easy. So we just go ahead and keep going. So we get this, and we get negative 8 plus 8. Remember, change sides, change signs. So we end up with 0 equals 0. It would be very nice to get it to that point and then claim that this is an identity. Therefore, the solution set is all real numbers. All right. So here we have an application of linear equations, and we want to find two consecutive odd integers such that 28 more than the lesser is 3 times the greater. The game plan for solving applications of this type will be to basically, first of all, understand the problem, exactly what is given and what is wanted. And then, so as a first step, we want to understand what is given and what is wanted. Then we want to go ahead and translate. Step 1 is also where we organize our information. If we've done step 1 well, step 2 becomes easy, and then finally we're going to solve. That's usually the easiest step. Now, we do understand that we're looking for two consecutive odd integers, and that we're given some information about how they're related to each other. This is in the category of problems called the comparison problem. And we notice that if we make a table in this way, there's a first integer and a second odd integer, right? And we then know either one, but I can go ahead and call the first one x, right? Now, since they're consecutive odd integers, I know that the next one is going to be 2 more, such as 3, 5, 7, 9, 11, 13, right? Or negative 13, negative 11, etc. So notice that the next one will be x plus 2. So I can use this table of values to now easily set up my equation, because I know that 28 more than the lesser. Remember, the first one is also the lesser one. The second one, which is 2 more than that, is going to be the greater one as well. All right, so 28 more than the lesser will be just x plus 28 is 3 times the greater. So 3 times, of course, the greater here is x plus 2. Okay? and we get x plus 28 equals 3x plus 6. So let's move the x's to the right side. So keep the 3x here, bring the x over so it becomes minus x. We're going to keep the 28 on the left side and bring the 6 over so it becomes negative 6. Remember, change sides, change signs. So now we get 2x equals 22. So x equals 11. All right, so the nice thing about this table is I can bring the 11 in and say, okay, that's x, so I know that the next one will be 2 more than that, so it'll be 13. So the numbers we're looking for are 11 and 13. All right, so remember, game plan. Understand what's given, what's wanted. In the phase of understanding, also organize your information, then translate. Of course, we don't mean from French to English or anything. We mean from English to mathematics. And then you're going to solve. And that's it. Now, do make sure after you solve that you answer the question asked. Okay? So answer the question asked, because sometimes it may not be the x value that you find. You may have to do a little something, right? For example, here we had to add 2 to get another one of the questions that they had. So always make sure that you read it carefully. All right, so that's that. Let's go ahead and take a look at another. So here we have a geometric type of application. We want to find the measure of an angle whose supplement measures 9 times its measure. First, we need to remember that if 2 angles are supplementary, like let's say angle A and angle B are supplementary, like this, then the sum of their measures is going to be 180. So it means if the angle B is solved for, we get 180 minus A, right? So if you want to make a table, you can say angle supplement. If the angle is A, the measure of the supplement is going to be 180 minus A. Okay, so we want an angle whose supplement, you can do an intermediate kind of equation if you want, is 9 times its measure. So the supplement is right here. So instead of sup, we put 180 minus A. And the measure of the angle, of course, is A itself. There it is. So you just have to solve this. So you get 180 equals, move the negative A to the other side. So we get change sides, change signs. So it becomes plus A. So we get 180 equals 10A. So A equals 18. And that's all we needed to find, the measure of the angle, right? So we are basically finished. All right, and that's that. So, right, so here's an application with regard to a certain kind of equation called a formula, which basically usually has more than one variable in it. And here we want to substitute these known values here. We know A, we know B, capital B, and lowercase b. Be very careful, the case matters in problems like this. and then we want to solve for the unknown variable. So if we just plug in, notice a is 36, so we get 1/2. We don't have h, so that stays, and we know capital B is 7 and lowercase b is 2. And see, that brings us to this situation where the only thing left is h. So that's what we're going to solve for. So here, if we just multiply both sides by 2 real quickly, we can get rid of that fraction. So let's do so. So we end up with 72 equals h times 7 plus 2. So we get 72 equals 9h. So h equals 8. Just like that. Alright, so you can see it's not too bad. Alright, so here we have another one which is geometric in nature, and here we're finding the measure of these two marked angles here. Remember, not x, but the angles. And we do note that these two angles are adjacent because they share a side, and they're complementary because they add up to 90 degrees. So basically the equation that's going to do this for us is 4x plus 9x minus 14 equals 90. So we get 13x equals 90 plus 14. So we get 13x equals 104. So x will be 104 over 13. And if we calculate that, 104 divided by 13, we get 8. Okay. Now, be very careful because you don't want to stop yet. That is not what is being asked for. You're being asked for those angle measures. So we can put those like this. So if you make a table where you have the value of x and you want 4x and 9x minus 14, it'll keep everything nicely organized. Okay, notice that x is 8, so 4x will be 4 times 8, which is 32, and here you get 9 times 8, which is 72 minus 14, right? So $58. All right, so the angle here, that's going to be 32 degrees, and this one is 58 degrees. You always want to do a quick common sense check. Notice that these two should add up to 90. Do they? Well, let's see. That's 80 and that's 10. So yes, they add up to 90. So that's the least amount of checking that you should do for something like this. All right. All right, so for this problem, we want to solve this formula for the variable c, and that's lowercase c. So we handle it very much the same way as any linear equation. So we go ahead and try to, we notice that the c is trapped inside the parentheses, so we go ahead and distribute. So we get w equals gc plus gt. Now we want to isolate the c term, so we keep the gc where it is. We'll go ahead and move the gt to the other side, and it becomes what? It becomes minus gt. Remember, change sides, change signs. And we're almost there. See, we want to solve for c, so we just need to get rid of the g, which we can do quickly by dividing it off from both sides. All right, so now we end up with c is equal to w minus gt over g, just like that. All right, so make sure you practice that and we'll move forward. All right, in this problem we're going to solve this linear equation in two variables for y, and that is something we will actually do quite often this term, so it's something you will want to get comfortable with. All right, so basically, since I'm solving for y, I'm going to go ahead and leave y alone, and I'm going to move x to the other side, so I get negative 3x instead of 3x because we changed sides, plus 15. Now we just need to get rid of the negative 4, so we divide both sides by negative 4. All right, so on the left side we now have y. On the right side, those split up, right? So you get negative 3x over negative 4, and then plus 15 over negative 4. So you end up with y equals, now negative over negative is positive, so you just get 3/4x, and positive times negative is negative, so minus 15 over 4, just like that. Okay, so that's all you're expected to do with a problem like this one. In this problem, we're going to write a given ratio as a fraction in lowest terms. Now, if the units are convertible, we should be able to get rid of the units altogether. All right, so we want the ratio of 100 seconds to 2 hours. Now, seconds and hours, as it turns out, are convertible. So what we're going to do is we're going to use what's called the unit factor. Okay, now we know that 1 hour is the same as 3600 seconds, right? So what we do is we introduce the unit factor in this way. We put the hour up here so that the hours can cancel out, right? And we want to put the 3600 seconds down here. So in this way, we notice that we can now cancel out the hours and the seconds, and we're just going to get a pure ratio. And we will also cross cancel as much as we can. 100 goes into itself once, into this one 36 times. So this is basically 1 over 72. So this is kind of a nice size comparison. So how does 100 seconds compare to 2 hours? Well, how does 1 compare to 72? You see, in other words, 2 hours is 72 times longer a period of time than 100 seconds. All right, so for this one we want to solve for y, and this time I hope you do notice the fact that here we have a proportion, and remember, anytime you have a proportion in mathematics of the form a over b equals c over d, that means you can cross multiply. That means AD is going to be equal to BC. right? So here we can cross multiply, so we get 3 times y minus 1 equals 5 times 4y plus 7. So if we keep going, we get 3y minus 3 equals 20y plus 35. And now let's get the y's on the same side. So 20y minus 3y equals negative 3 minus 35. So we get negative 38 equals 70y. So y equals, basically divide both sides by 17. If there's any simplification that's possible, we attempt it, but here there is nothing else we can do, and this should be it for us. All right, and make sure that you can handle a problem like that on your own, please. So here we're going to be solving an application of proportions. The distance between city A and city B is 1600 miles on a certain wall map. This is represented by 6.4 feet. On the map, how many feet would there be between city D and city E, two cities that are 2000 miles apart? So we set up a proportion for these in such a manner. We say if 1600 miles corresponds to 6.4 feet, then 2000 miles would correspond to how many feet? This is one of the most useful types of applications in mathematics. You'll use it in all kinds of different scenarios. Proportions are extremely useful. All right, so now we will go ahead and just cross multiply and solve, and that can be easily handled. So we get 1600x equals 2000 times 6.4. Notice we are just cross multiplying. So we get x equals, divide both sides by 1600. And then we can just go ahead and utilize a calculator. Okay, so we have 2000 times 6.4 divided by 1600. So, and that is 8. So basically the city, the distance between city D and city E will be represented by 8 feet on that map. So of course your final answer should always have the proper units. All right, so just like that, very straightforward. All right, so now we want to look at a few percent applications. We want to know 55% of what number is 88. The best way to approach these, the way that you're never going to forget, is just direct translation from English to mathematics. So basically the 55% here obviously is going to translate as 0.55, because remember 55%, that means 55 over 100, which is 0.55. Of translates to times. What number is going to translate to x? Is going to translate to equals, and then 88. This is the most natural way of setting these up. Okay, so then all you have to do is solve for x. So we go ahead and divide both sides by 0.55, and we get x equals, now we're just gonna use our calculator. So we have 0.55 times 88. Oh, the other way around, sorry. Correction. 88. We're doing this calculation. The one here. So 88 divided by 0.55, so we get 160. So 160. So 55% of what number is 88? 160. It's very easy to check that, right? Here's what we'll do. We'll just go 0.55 times 160. We better get what? We better get 88, which we do. Okay? And that's that. And it kind of makes common sense as well, because that's around where that should be, right? Half of, you know, it's very close to half. So half of what number is 88, right? Type it like that. Okay. So always do a common sense check. Make sure that it makes sense in that way as well. So there we go. Now let's look at one more percent problem. All right, so for this one we have what percent of 20 is 50. Again, we can do a direct translation. This one is a little bit more interesting, because here's what's going to happen. We're going to say what x percent, that's over 100, right, of times 20 equals 50. That's it. We're going to solve that and we'll be in great shape. All right, so 20 and 100, they're on the same side, and they're numerator and denominator, so we can cross cancel. So now it becomes a lot simpler. So we get x over 5 equals 50 over 1. So now we cross multiply to solve. So we get x equals 250. So what percent of 20 is 50? Does it make sense that the answer is more than 100? Yes, because look, 50 is more than 100% of 20, isn't it? It's in fact more than 200% of 20, because what would 200% of 20 be? It would be 40, right? That would be twice 20. That's 40. So this makes complete sense. All right, let's go ahead and look at one last percent problem. It says, what is 25% of 200? Okay, I think you have a hang of it by now, right? You need to be going ahead and setting up an equation. So 25%, so that's 0.25. Okay, let's do it precisely like we've been doing. What is? So x equals, right? 25%, so 0.25 of 200. It's good to be consistent, then you're less likely to make mistakes. So we get x equals 0.25 times 200. That's just a quarter of 200, so 50. There we go. All right. So remember, the best way to solve these percent problems, just directly translate them from English into mathematics and solve. All right, now we're going to get ready to solve inequalities. Before we do, we need to understand a couple of different concepts. One is the fact that the set of real numbers has two kinds of subsets. Discrete subsets, such as the set of natural numbers, whole numbers, integers, where there are gaps between the elements of the set, right? Like there's a big gap between 1 and 2, right? In fact, you can fit infinitely many numbers between 1 and 2. So that kind of set where there are gaps between the elements of that set, that's considered a discrete subset of the set of real numbers. And then there are some subsets of the set of real numbers, such as this one, the set of all basically numbers between 0 and 1, like this. Notice that this one is what we call a continuous subset of R, because there are no gaps between the elements of this particular set. So if you pick any two numbers in this set, you will find there are other members of the set between them. Okay, so in fact, the mind-blowing part is that you'll find infinitely many real numbers between any two distinct real numbers. Even if you take the number from 0 to 0.1, all right, you can easily find infinitely many numbers inside there. How do you do that? Well, take the number halfway between 0 and 0.1. Then take the number again halfway between 0.0 and that new number that you found. And this process can go on and on and on and on, right? So basically, we called those subsets continuous subsets of the real continuum itself. The set of real numbers, of course, has no gaps. Everything is contained in the set of real numbers. It's truly a magical wonderland. Here's a couple of other interesting ways of showing, for example, that there are infinitely many numbers between 0 and 1. What about this group of numbers? Take 1/2, 2/3. Here I'm going to add 1 to the numerator, 1 to the denominator. 2/3, 3/4, 4/5, 5/6. This process never ends, all right? And all of these are proper fractions which are between 0 and 1. And there's obviously infinitely many of them. You're never going to run out of such fractions, right? Here's another way. How about we take the number 0.1 and then 0.11 and then 0.111 and then 0.1111, right? How many numbers like that are there? Well, there are infinitely many of those. And notice, you don't even have to go between 0 and 1 to get infinitely many points. This is, all these numbers are basically between 0.1 and 0.2, all right, including 0.1 and 0.2. But there are infinitely many numbers just between those two numbers. So there's no shortage of real numbers, right? So these connected continuums of real numbers, like the set of all real numbers between 0 and 1, are encountered often in mathematics. So it'd be nice to have an efficient way of representing them. Interval notation is exactly what provides us with that elegant and efficient way of representing continuous subsets of R. So the set which says all real numbers such that x is between 0 and 1, in interval notation just becomes this. See, this is exactly the same as this, but in a much more compact kind of notation. This, of course, should not be confused with the ordered pair 0, 1, which looks identical but is very different, and it will always be understood in context whether we're talking about the point 0, 1 or the ordered pair 0, 1. All right. This notation here itself has a name as well. This is called set builder notation. The reason for that is because here we're not listing the members of the set. We're not listing the numbers between 0 and 1. We're giving instructions for how to build the set, right? We're saying, hey, pick all the numbers between 0 and 1. That's your set. That's an instruction. That's not an actual statement that's providing us the specific elements in that set, correct? So both of those sets are very important. Those set notations, I mean, are important and used very often. All right, so when we view an interval like 0, 1, these 2 points, 0 and 1, they're called endpoints of the interval. When we do not want to include the given endpoints in a set represented by an interval, we use a parenthesis next to it. When we want to include it, we will use a bracket next to that endpoint. Here we're going to look at various finite length intervals. Notice that when we say finite or infinite with respect to intervals, it's always about the length. It's never about the number of points in them. You know that all intervals have infinitely many points in them. So how about what if we first describe it in words, then we write it in set builder notation, then interval notation, and we give it a name, and then we graph it. So here we're looking at all real numbers between 2 and 5. This, of course, would exclude 2 and 5, this set. So basically in set builder notation, that's all x belonging to R such that x is between 2 and 5, just like that. Now this would be called an open interval, and we would say open interval 2, 5, and we would graph it like this. It would be open circle at 2, open circle at 5, and we just connect the segment just like that. So there is the set in blue right there. How about all real numbers between 2 and 5 left inclusive? Well, this one means include the left endpoint 2 but not the right endpoint 5, right? So this would be half open interval 2, 5 because it's closed on one side but open on the other side. So notice it's going to have a bracket on the 2 side because the 2 is included, and it'll have parentheses on the 5 side because 5 is not included. And what if we want all real numbers between 2 and 5 right inclusive? So this time we're going to include the 5, but we're not going to include the 2. So this is again a half open interval from 2 to 5, and we have open arrow, open circle at 2 and closed circle at 5. And what if we want all real numbers between 2 and 5 inclusive? That means we want both endpoints in there, right? So notice that since we want both included, we're going to have brackets on both sides and closed circles on both sides of the graph. And these are all the different ways we could deal with these finite intervals. Okay, next we're going to look at the types of infinite intervals that you will encounter. And of course we mean infinite in length. We know that all intervals have infinitely many points in them. So we start with all real numbers greater than 2. So basically the best thing to do is go ahead and graph it. It'll make it easier to write both of these notations. So greater than 2, that means open circle at 2, arrow to the right, right? Because everything here is going to be included. So so the set builder notation is just going to be all x belonging to R such that x is greater than 2. For interval notation, remember you always want a starting point and an ending point. Well, this one has a starting point. It starts at 2, but where does it end? It doesn't. That's where you see the comma infinity come from. So remember, because of the fact that infinity is not an actual number but a numerical concept, you never include it. So you're always going to have a parenthesis next to an infinity, as well as to the left of a negative infinity for the same reason. Alright, what if we want to look at all real numbers that are greater than or equal to 2? So this time we're going to include 2 in the set. So it'll look like this. The only thing that changes is the greater than here becomes greater than or equal to 2, and the parenthesis here becomes a bracket, because that's what we use when we want to include an endpoint. And again, it starts here but it doesn't end, hence the comma infinity. Now we want to look at all real numbers less than 2. So it's all x belonging to R such that x is less than 2. So where does this interval begin? See, do a graph, it'll make a lot more sense to you. It has no beginning. That's why you have negative infinity as the starting point, comma, but where does it end? Yeah, it does end at 2. So there you go. Does it include 2? No. That's why you have an open circle. Okay? And then all real numbers less than or equal to 2, well, that's just going to change to this. Here the parenthesis is going to change to bracket, and here the circle is going to be closed. Everything else is the same. Once again, starts at negative infinity, ends at 2. And that's basically it as far as intervals are concerned. Alright, believe it or not, we're nearing the end of this long video. We're going to finish with solving linear inequalities. Now, when it comes to solving linear inequalities, they're very similar to solving linear equations, with one exception and one recommendation. The exception is a mandatory difference in approach, and what it states is that if you multiply both sides of an inequality or divide both sides of an inequality by a negative number, you need to switch the direction of the inequality. If it's a less than, you're going to immediately turn it into a greater than, and vice versa. Why is that? Because see, 1 is less than 2, isn't it? But if you look at negative 1 is not less than negative 2. Negative 1 is actually greater than negative 2. Why? Because negative 1 is on the right of negative 2. You see that? But 1 is definitely less than 2. So when you multiply by negative, things get interesting. The other exception is a recommendation, actually. So, but it's highly recommended, and that is that when you're at the separate stage, you know how we separate the variables from the constants, always move the variable terms to the left side, okay? Because sometimes when we're solving equation, we move them to the left side, sometimes we move them to the right side, depending on where the coefficient is larger. Don't do that with linear inequalities. Always move the variable terms to the left side. And the reason for that is that this is much easier to read, interpret, and graph than this. So that's why the recommendation to do so. Alright, next we want to take a look at these two problems. The one on the left is pretty straightforward. There's nothing to simplify. We're ready to separate. So we're going to go ahead and keep the 3x on the left side and move the negative 5x from the right side to the left side, where it will become plus 5x. So we have 3x plus 5x less than or equal to, we'll keep the negative 3 on the right side and move the negative 5 to the other side, so it becomes plus 5. So we get 8x is less than or equal to 2. Divide both sides by 8. And there's no need to change the direction because we're not dividing by a negative number. These cancel out. These leave you 1 and 4. So we end up with x is less than or equal to 1/4. In order to write the set of this problem, the easiest thing to do for any solution set, once you've solved the inequality, draw the graph first. So you can see here we're going to have 1/4 and a full circle there, and then less than or equal to means arrow to the left, right? So we're interested in describing these numbers in a problem set. So as far as set builder notation is concerned, that's simple. That's just all x belonging to R such that x is less than or equal to 1/4. For the interval notation, we notice that we always want the beginning point and the ending point, and this is one of those cases where there is no beginning. So in other words, this one is beginning at -infinity. So we say parentheses -infinity comma 1/4, and we're including 1/4, so we will use a bracket just like that. Okay, so very, very simple. All right, for this next one, it's not that much harder. It's just there's some, you know, simplifying that we need to do on each side. So we go ahead and start with 4x, and now we're going to distribute the invisible 1, remember? So we end up with minus 7x minus 5 less than or equal to 8x. Now we're going to distribute the 4, so we get plus 4x minus 16. All right, so now we have negative 3x minus 5 less than or equal to 12x minus 16. So we're going to keep the negative 3x here, move the 12x over, so it becomes minus 12x, and we're going to keep the negative 16 on that side, and move the negative 5 to the other side, well, it'll become plus 5. Okay, so now we have negative 15x is less than or equal to negative 11. Now we're going to divide both sides by negative 15. And in order to do that, I'm going to go to a new line because something needs to happen, as you know. The moment I divide both sides by negative 15, I have to also switch the direction of the inequality, because you always have to do that whenever you divide or multiply by a negative number. So we end up with x is greater than or equal to, notice that's just going to become positive 11 over 15. All right, so basically we have 11 over 15 on the graph, and we're going to want a closed circle, and then greater than means we're going to want an arrow to the right. Okay, so the set builder notation here will be s equals all x. Sometimes we don't put the plus r, assuming that it's clear, such that x is greater than or equal to 11 over 15. And for interval notation, we notice this interval does have a beginning, but it has no end, so it's moving toward positive infinity. So it's going to be bracket 11 over 15 comma infinity parentheses. We never put a bracket to the right of infinity or to the left of negative infinity, and that should do it for these two problems. Okay. All right, and here is our last problem for the day. This is what we call a three-part inequality. It's actually two inequalities lumped into one as a conjunction, which is an AND statement. So here, notice that that is one inequality, and this is the other inequality that we're solving simultaneously. We do it because the steps involved are actually pretty much identical. So basically, the first thing we'll do is we'll go ahead and clear the fraction by like we would with in the case of equations when there are fractions. The best way to approach them is to clear the fraction, and we'll do that by multiplying all three sides by 4. That's the thing about these three-part inequalities. Anytime you do something to one part, you got to do it to all three parts. So we're going to multiply 4 across the board. All right, so 4 times negative 10 and 4 times is going to be less than, here we have 1/4 z plus 1, and here we have less than or equal to, just like that. Okay, so we end up with negative 40 less than, now we're going to distribute this 4, so you get 4 times 1/4 is 1, so 1z, and 4 times 1 is 4, so plus 4 less than or equal to 4 times 8, which is 32. Okay, so now we are going to have to get rid of the 4, because remember we're solving for z, right? So we're going to go ahead and subtract 4, but that means we need to subtract 4 in all 3 spots. Okay, and now we end up with negative 44 less than or equal to z less than or equal to 28. And that is the way we're going to solve this, present the solution set. Well, in set builder format, it's very easy. It's just going to be all z belonging to r, such that negative 44 less than or equal to z less than or equal to 28. And if we graph the situation, basically we want everything between negative 44 and 28. Okay, we need to make a correction. That's not less than or equal to. Somehow I picked up an or equal to somewhere. No, it's less than. So open circle at negative 44, close circle at 28. So be careful. When I went from this step to this step, I accidentally added or equal to. It wasn't there. Okay, that doesn't suddenly change to less than or equal to. All right, and now we're gonna also want everything in between. So the interval notation for this is going to be parentheses negative 44 comma 28, and on that end we need a bracket because it does include 28. All right, so actually I'm glad that I made that error so that you could see how easy it is to do that, especially with the ones which have mixed strict inequalities as well as inequalities. So be very, very careful with that, okay? And one of the things you want to do on a test is always double check every answer. That way you'll catch any such carelessness. All right, and that pretty much does it for us. So stay safe until our next video.